right. We're going to talk about resistors. We should have talked about this last week, but that's okay. And now I can't move the slides. Great. Now, oh, it's hiding behind that. Oh, okay, cool. All right. All right, so we're going to learn about resistors. We're going to talk about fixed resistors. And the main thing we're going to do is we're going to be able to determine the resistance, the nominal resistance of a resistor, and its range. What is in range for that resistor according to its color code? We're going to discuss the purpose of adding resistance to a circuit. We're going to discuss how exceeding its power rating can cause damage to a resistor. I don't think that takes much discussion at all. Overheating anything does what? Does damage to it. Discuss the use of variable resistors as a potentiometer, or however else we're going to do it. All right. And we're going to talk about carbon composite resistors, metal film resistors, carbon film resistors, nonlinear resistors, varistor, and thermistors. Okay, now a series circuit, as you know, that you're putting resistance has two purposes of putting a resistor in there. The number one purpose is to reduce the current. Now look at the drawing on the bottom on the left and imagine that that is a 0 to 500 ohm resistor and that you have a 12-volt battery supplying this thing. Okay, so how much current will it flow at 1 ohm? 1 ohm and 12 volts. How much current is going to flow? EIR, right? E divided by R. So 12 divided by 1 is 12 amps, right? Now let's turn it all the way up to 500. Get out your calculator. I know this is going to be very difficult. 12 divided by 500. It's going to be way less than 1, right? So as we've dialed this variable resistor up from 0 to 500 ohms, we went from 0 resistance, or 1 ohm resistance, and we flowed 12 amps of current. Now probably we just blew up the resistor because it won't take 12 amps, probably, because it's wattage rated. 12 amps times, what's power? P-E-I. 12 times, what's the current? 12 times 12, 144, right? Okay, most resistors are rated at 1 or a half or 5 watts or 25 watts. So if we're flowing 144 watts, we've probably just burned up the resistor, right? So let's turn it up now. Let's just try a different spot. Let's turn it up to 12 ohms of resistance. How much current is flowing at 12 ohms of resistance? 1 amp. So just from going from 1 to 12 ohms, we went from flowing 12 amps down to 1 amp. You see what's happening? If you hold the voltage steady and you turn the resistance up, the current goes down. So if you put a fixed resistor in there that's got 6 ohms of resistance, what is your current flow? 2. Half? What? I don't know. 2 amps? Okay. So you can see that as you turn the resistance up, the current goes down. It's what we call an inverse relationship. Turn up the resistance, the current goes down. Now let's look at our drawing on the far right, which is not very good. So we're going to go to this next one, and we're going to look at 3 resistors in series. And you can see that we have different voltage drops across resistor 1, resistor 2, and resistor 3. We have 30 ohms, 120 ohms, and 200 ohms, and we have a set supply, and a certain amount of voltage is going to be dropped across 1, 2, and 3. So we can see the voltage being dropped across resistor 1 is 1.5 volts. Our voltage across B to C is 6 volts. And our voltage drop across C to D is 10 volts. So if I wanted 6 volts to supply something else, I could connect to B and C, and I would have a 6-volt supply across that. Isn't that odd? But that works that way. As a matter of fact, that's basically what's in your little cigarette device that you put in your car that powers your cell phone. Because your cell phone doesn't want 12 volts, it only wants 3 volts. And it wants DC, so that's a good thing. It needs to knock the voltage down. How do they do that? With a pair of resistors. Okay. Now, let's go to the next slide. We're going to talk about basic fixed resistors. They have only one resistance, and it will change over time as it gets old, number one, especially if you're talking about a carbon resistor. And number two, it will change a great deal if you overheat it. All right? So that's what happens with those. Why is it the most common resistor in the world, though? Somebody take a wild guess. Cheap! Exactly correct. Because it's the cheap way to do it. Okay? And by the way, if you look at this slide later, I want you to notice it's got color bands. It's got numbers identifying the color bands. It's a really good little drawing. Okay? And then we have carbon resistors again. But I wanted to show you what one looks like. And a carbon composition resistor is essentially the same thing, by the way. Let me move this thing out of the way. And what do we know about carbon composition resistors? They're essentially a carbon resistor also. It's just got very few things different about it. Okay. And here we have a metal film resistor. You'll see them in the lab next semester. They're fairly common, and they're not quite as cheap as a carbon resistor. They're a little more stable as far as the resistance. They don't start diving in resistance as they get old, just because they're sitting around for a long time. Carbon resistors will just start losing some of their resistance or gaining resistance, one of the two. And a metal film is a little tighter resistance range, I should say. A wire wound resistor is a very simple device. They take a tube, they ceramic coat it so it's impervious to the heat. They wrap wire around it, and the wire is not copper wire. They wrap it with what I call thermocouple wire. If you make a type J thermocouple, you make it with iron and Constantan. And the reason they use iron and Constantan is the heat doesn't affect the wire as much as it would for copper wire. Very important thing when you're trying to flow a lot of current is creating a lot of heat, because heat would normally change the resistance of copper wire, right? Well, with iron and Constantan, it's just not true. So you can have a lot more current flow with iron and Constantan power resistor. They're called power resistors because they will operate at a lot higher power. If you're looking for more than 25 watts, you're probably talking about a wire wound resistor. Okay? Now, one of the things I do want you to take notes on now or sometime soon after you see this thing a second time is that the range of resistance values varies from 1 ohm to 1 mega ohm. Typical tolerance of these resistors varies from 0.01 to 1%. What does that mean? That's a really tight variance, isn't it? Really tight range. 0.1 to 1%. That's a really good resistor. Okay? And they have high power ratings of from 5 to 200 watts. So please write those sets of numbers down. You may see them again someday. Okay. A non-linear resistor. This is an MOV that I'm showing you a picture of here. It's a non-linear. It's a semiconductor, and that means the current going through depends on the non-linearity of the applied voltage across it. So as the voltage goes up or down, it will change. This is actually a metal oxide varistor, and it does something in a lot of circuits there. If you have a blue receptacle at your office, a blue receptacle, that means that it has MOVs in it, and if you get a spike coming in from Edison, the MOVs will eat the spike, but it also tears away part of the MOV, literally. It destroys the MOV as it goes, but the spike doesn't come through the receptacle. That's a really neat receptacle, right? It's also about a $40 receptacle. But if you've got, let's say, a $10,000 computer and you're plugging it into a receptacle, you probably don't want to plug it into a non-MOV receptacle, do you? So if you have a Cray computer, you're probably going to plug it into a $40 receptacle. Okay? There's a formula for the function of the applied voltage, and the current is equal to K times the voltage times alpha. So there we go, big formula. Okay, variable resistors. There are two kinds, the potentiometer and the rheostat. You do need to know that one of them is 2-wire and one of them is 3-wire. Look at that slide and tell me which one has 3 wires. A pot has 3 wires. A pot, they call it, has 3 wires. A rheostat is it has the same terminals. Here, my little thing is in the way again. You'll notice it has 3 terminals. Well, a rheostat is the same device, except it's got a connection here and a connection here. And that's all. It's not connected to this one at all. So as the current goes through here, it literally just goes right through this device. Okay? A varistor, we've already talked about one kind of varistor, an MOV. And there we have the symbol for a varistor, if you happen to see one. And there we have a cute little picture, and it looks just like that last picture of one. Okay, and this is a different kind. Okay, let's talk about the color code. Now, you guys have done the homework on this already, so this should be no surprise to you. Things in the way again. Can I keep it out of the way? Okay, I know I don't want to do that. I might need to stop it quickly. Okay, so once again, our numbers are on the far left. Our first number is always, the first 2 numbers are always first and second digit of the number. The third one is sometimes a digit of the number, and sometimes it's a multiplier. If it's only a 4-band, the third one is the multiplier. The last one is the odd duck in the group. And by the way, I want you to notice that in this one, it has silver and gold in the multiplier. What does silver mean? Now, black is 1. That's 10 to the 0, right? So if that's 1, then gold must be 10 to the minus 1, 10 to the minus 1, and silver is 10 to the minus 2. So if you write it down, black, brown, red, orange, yellow, green, blue, violet, and then add gold at the top and then put silver on top of that, you can go back up so that as though you were going down the engineering notation chart. And so at your base unit, you have 10 to the 0. 1 below that, we're going to assume that in this case we have 10 to the minus 1, and silver is 10 to the minus 2. Okay, those won't come up today. They might come up some other day, though. Now look at the tolerance bands. It's always got gold and silver in it. Gold and silver are very common. Gold is not very good. It's plus or minus 5%. Silver is horrible. The only thing worse than that is not having a tolerance band where it's 20%. If you only have 3-band resistor, it's a 20% resistor. That means it's a real piece of junk, right? 20%, plus or minus 20%. That means a 100 ohm resistor with 20% variance can be as low as 80 and as high as 120. That's not exactly what I would call close. That's not even the ballpark, in my opinion. but that's a whole different open. So brown is 1%, red is 2%, green is 5%, blue is 0.25%, and violet is 1/10 of 1%. Now the green, blue, and violet are really unusual. You and I may never see a resistor with those tolerance bands because those resistors are getting real expensive, right? It's that one almost perfect resistor out of the batch of thousands of them, right? They're going to charge a lot more for that one perfect one than all the rest of them, right? Oh, look, we got one perfect. Okay, we got a little handful of perfect ones. Out of 1,000, they'll literally only get a few. Okay, so yes, you need to know all of this except the temperature coefficient. You do not need to know the temperature coefficient. But the rest of this you actually need to know. Now, what we're going to do now, we're going to do a little practice. Now, what is the nominal value? Look at that top resistor. I can't even hardly see that darn thing. Okay. I don't know how I can pull that up without showing you everything. Let me hit pause for a second. Okay, so our first resistor is green, blue, black, black, brown. Our second one is red, red, orange, gold. Our next one is yellow, violet, brown, gold. And our last one is blue, gray, black, gold. So on our first one, Roman, do you know what the first one is in resistance?
5.
Nope. The very first one. The very first number is 5, but what's the whole number? The whole resistance. The nominal value of the resistance. 560 is correct. Raimundo, what is the tolerance associated with brown as a tolerance band? Plus or minus 1%. No, it's plus or minus. Plus or minus 1%. So that first resistor is a 560 plus or minus 1%. Okay. What is 101%? 1.01 times 560. Do what? No, 1.01 times 560. 101%. 565.6. So that resistor could be as high as 565.5 on the top end and as low as, how would we find the low end? Multiply 560 by 0.99. 99% is 1% low, right? So 560 times 0.99 is what? 5 what? 554.5. Watch the fingers. Okay, so the next one. Alex, tell me the resistance, nominal resistance only, of resistor number 2. Second resistor, red, red, orange, gold. What number is red, red, orange? What number does that give us? Well, that's close. Orange is 3, isn't it? So 10 to the third times 22. 22,000. We don't say 22,000. We say 22K. 22K. 10 to the third is K. Okay. So 22,000 times 1. Now, wait a minute. What is our percentage with gold? 5%. So 105%, 1.05 times 22,000 is what? 23,100? I thought it was 23,002, but okay. Okay, now what is 5% low? That's 95%, right? So 90.95 times 22,000 is what? 20,900? Okay, good enough. All right, let's go to our last one. or second to the last one, I'm sorry, yellow, violet, brown, gold, which I would have never parsed that out of that looking at that. All right, Jack, tell us what the resistance of that one is. 470 ohms. Don't tell us anymore. Now, if it's got a gold resistor, a gold tolerance band, what is its tolerance? Jack, go ahead. 5%, that's right. So 1.05 times 470 is what? 493.5. That's the highest it can be. If it's 493.6, that's out of range. Okay? 470 times 0.95 is what? 446.5. That's right. And so if it's 446 ohms even, it would be out of range low. Okay, our last one, blue, gray, black, gold. Let's see, somebody. Mr. Miller? Oh, I'm sorry. Sorry I said your name. You're going to be in the recording now. Is that okay with you? Okay. What is the nominal resistance if it's blue, gray, black? Right on. Now, if it's got gold for a resistor, seems like a lot of these were gold, doesn't it? Remember I told you that's the most common one. Okay. So 68 times 1.05 is what? 71.2? Good enough. How about 95%? Okay, so now we know how to figure the range, right? Everybody knows how to do that. Anybody not sure how to do that? Okay, we're gonna stop now. That's what we want to do. We want to do a little practice.